The next ones are distance, rate, and time problems, and they're going to mix up a couple different kind of distance, rate, and time problems together in the same section. Main thing they want to get across is that rate times time is equal to distance, and I want to use that to solve my problems. One of the ones that we're going to be doing is when you're going like against the wind and with the wind, where the rate is either going faster or slower depending on what's pushing against you. It says a cyclist travels 22 miles in 2 hours going against the wind. She travels 42 miles with the wind in the same amount of time. What is the rate of the cyclist in still air? What is the rate of the wind? So I'm going to have two different rates. I'm going to say the cyclist and the wind. And if I'm going against the wind, in theory, I'm going to have the cyclist minus the wind because the wind's pushing against me, making me go slower. If I'm going with the wind, I'm going to have the cyclist plus the wind because the wind's going against my back and making me go faster in theory. So that's going to be my rate. My rate times my time is equal to my distance. So I'm going to take my rate times my time. The cyclist travels 22 miles in 2 hours going against the wind. So my time here, 2 hours. My distance, 22. She travels 42 miles with the wind in the same amount of time. So still 2 hours, but this time I went further. I went 42 miles. So what they're going to do with these ones is they're just going to go ahead and divide by the time right away so that they can get the rates, the variables, by themselves. So I'm going to divide by 2 on both of these. My top equation then, C minus W equals 11. My bottom equation, C plus W equals half of 42, which would be 21. Now I have one of those like we had when we did the sum and the difference were these two different numbers. I can just go ahead and add my two equations together because that's going to cancel out the W's. So 2C is equal to 32. If I divide that by 2, C equals 16. So the cyclist is going 16 miles an hour. I still need to find the rate of the wind. Again, I like to use the one with the plus because then I just have to subtract the 21 minus 16. So if I subtract there, what would I get for the rate of the wind? Five, right? So the cyclist is going 16, the wind is going 5. So usually on these ones, they'll just go ahead, instead of using the distributive property, just divide by the time right away, then it makes it pretty easy to solve. Now the other kind that they're going to do is your normal rate times time equals distance problems where you've got two trains going opposite directions or whatever it might be. Two buses leave towns 228 miles apart at the same time. They travel toward each other. So one's going to go this way, one's going to go this way, and eventually they're going to meet in the middle, or not quite the middle, but somewhere in between. One bus travels 16 miles an hour faster than the other. So one's rate I'm just going to call R. The other one's rate, R plus 16, right? It's going faster. They meet in 2 hours. What is the rate of each bus? I know that rate times time equals distance. So they met in 2 hours. The rate times 2 here. The rate, which is R plus 16, times 2 there. So simplifying that, 2R plus my 2R plus 32 would equal the total distance between the two buses, 228 miles apart. Now I have an equation that should be fairly easy for you guys to solve. So 4R plus 32 equals 228. If I subtract my 32, 4R is going to equal, make Gavin do all the work today.
196.
196? And if I divide that by 4, what was that?
49.
49. I was looking up there and I even forgot it was 49, wasn't it? I probably should have had these other way around because obviously the faster one's going to be the plus 16 and the slower one's going to be the other way. The slower one would be R. The faster one's going to be R plus 16, right? Not that it mattered on solving my problem, but 49 would be the slower one. The faster one, 49 plus 16.
65.
65. And the last one then. 2 buses leave a station at the same time and travel in opposite directions. One bus travels 12 kilometers per hour slower than the other bus. So the rate of one bus is going to be R, or whatever variable we decide to do. The other one's going to be going 12 kilometers per hour slower. So R minus 12, right?
12, yeah.
And that would obviously be the slower one. It's going 12 kilometers per hour slower. So I have my rates of my 2 buses. The faster one's going R, the slower one 12 kilometers per hour slower, so R minus 12. 2 buses are 654 kilometers apart after 3 hours. So one of them is going 3 times R minus 12. The other one would be going 3 times R, right? So if I go ahead and distribute that out, 3R minus 36 plus my 3R is going to equal the total distance they are apart, 654. So 3R plus 3R would give me 6R minus 36 equals 654. So obviously we need to add our 36. 6R is then going to equal what?
690.
690. And 690 divided by 6 would give me
115.
115. Seems like a lot, but it's kilometers per hour, so hey, it's possible. So the faster bus is going 115 kilometers per hour. The slower one is doing 12 kilometers per hour less, so if we subtract 12, we get 103, right? Sure, you guys are yawning and sleeping and I believe that's the last of that page of homework.